Hey engineers, and welcome to Introduction to Thermodynamics. Today we're going to talk about thermodynamics and what it is. Spoiler alert, it's when heat moves from point A to point B. We're going to talk about how heat can go from point A to point B. We're going to talk about how to calculate how quickly heat can go from point A to point B. And within engineering, we use thermodynamics a lot within insulation. In a lot of different applications, we need to keep heat in or we need to keep heat out. So we don't want heat coming in, or we got it inside the building, we don't want it leaving, depending upon what season it is. And we're going to learn to figure out how to calculate how good an insulation is, and then how quickly heat can go from point A to point B. So let's get started. And by the way, as we're going through all of these today, I really need you to be taking notes. You're going to get a worksheet the next day, and it's going to have you recalling a lot of these definitions, recalling a lot of these equations that we're going to use today. So please, I need you with a piece of paper, and I need you with a pencil. And as I go through these definitions, you can have the written notes where you're just filling in the blanks, or you can just write everything on a blank piece of paper. It doesn't matter as long as you're getting these definitions down as you're going through here. So let's get started. Thermodynamics. They talk about having you rub your hands together for 15 seconds. That's friction, and you're generating heat, and that's what we call thermal energy. Thermodynamics is this. It's heat, that's what thermal, and then dynamic means movement. It's the study of how work, heat, and energy moves. Energy engineers use thermodynamics in systems ranging from nuclear power plants to electrical components. Thermal energy versus temperature. Thermal energy is measured in joules, and it's how much energy is going from point A to point B in transit from one object to another, because there has to be a temperature difference. Temperature is the measure of the kinetic energy in the particles. So if something is hot, the particles are bouncing around really fast. They have a lot of speed, and that's what we call temperature. Temperature is the average of all of the speeds of the molecules, and energy is what's transferring. So this has temperature. Heat is going to flow to the colder thing. The heat that we flow we call thermal energy, and the temperature is how fast the kinetic energy of each of the particles inside of the object. We've got a few different units of measure for temperature: Celsius, Fahrenheit, and Kelvin. In Celsius is actually based on the boiling and freezing of water. So it freezes at 0, it boils at 100. Fahrenheit, it's at 32 and 212. And then Kelvin, you just add, I think, 241 or something like that, to go from 273. You add 273 to Celsius to go to Kelvin. So this is just, when you have 0 Kelvin, that's when I was talking to you about temperature, if the molecules physically stop, that's what 0 Kelvin is when they stop moving. Thermodynamic equilibrium. Equilibrium is when things are equal. When you have a hot thing and a cold thing, and you have them touch, that hot thing and cold thing eventually reach some equilibrium. Like if I put a pizza in the room, a hot pizza, the pizza would lose heat to the room, so eventually the pizza would cool, but the room temperature would come up and they would reach some equilibrium. The room isn't probably going to go up much because there's such a difference in mass between the air in the room and the mass of the pizza. But thermal equilibrium is when you reach some middle ground. The Zeroth law of thermodynamics. It's kind of the transitive property. If these two things, if A is in equilibrium with B and B is equilibrium with C, that also means that A and C are in equilibrium with each other. It's kind of like the transitive property. If A then B, and if B then C, well then A then C. There's 3 different ways that heat can go from point A to point B. The most common one is convection. Another one is conduction. And the third one is radiation. Convection, conduction, and radiation. And we'll talk about those a little more specifically here. The first law of thermodynamics, it says energy can neither be created nor destroyed. That's the first law of thermodynamics. Energy can never be created or destroyed. It only changes hands. It only goes from one point to another. A bicycle pump, for instance, if you've ever pumped up a bicycle pump and it gets hotter, you're converting mechanical energy, like you're physically moving that pump up and down, and then you're pushing air. The total increase in energy is equal to the amount of mechanical energy. The second law of thermodynamics, heat only goes from hot things to cold things naturally. You can force it the other way, but you have to put work into the system, like a refrigerator. That's kind of how they work. So, for instance, you've got ice cubes. People are like, oh, ice makes my drink cold. No, really what's happening is the heat from your soda or water is going into the ice, so it's losing its heat, which makes it cold. Hot, it's going from hot to cold. Like a pizza, when it's frozen, and energy is going from the surroundings into the pizza. It's going from the hot thing, which is the surroundings, to the cold thing, which is the pizza. But now you cook that pizza. Now the hot thing is the pizza, and it's going into the surroundings. Energy is going from naturally. When left to its own devices, energy typically flows. It always flows from hot thing to cold thing. The second law of thermodynamics, we talk about what's called entropy, and maybe I'm sure that you talk about this in chemistry, when you tend towards disorder. Like in thermodynamics, you go from something that's more orderly to something more disorderly naturally. You can go the other way, but you have to put work into the system to do that. Going back to the three different ways that energy can go, there's convection. Convection is when hot things go up, which forces the cold things down. That's totally gravity driven. So if there wasn't any gravity, like up on space station when they're in quote-unquote zero gravity, there is no convection. Hot stuff stays where it is. Like the fact that gravity makes the hot things rise because it's making the more dense cold things fall, which forces those things up. Some examples would be if you have like a hot water heater or like these old school radiant heating, or if you have new school in-floor heat, that's convection. Hot stuff going up, cold stuff going down. Sun heats our earth, hot air rises, which causes the winds. That's all convection driven. Conduction, that's heating two things that are touching. If you are physically touching, like you've got a hot soup and you put a spoon in there, this spoon will get hot eventually because they're touching and the heat works its way up the spoon. Fun fact, just putting a spoon inside of soup is a way of cooling it because the heat's going from the soup into the spoon. How do we calculate how energy travels? So those of you that have been through physics, you've seen this equation before. This is how to figure out how much energy, so Q represents energy, how much energy is transferred when something changes temperature. Like if you go from hot to cold, like it's cooling down, that means it's giving its heat somewhere else. How much heat does it give it? Well, number one, it depends on how much mass is there. That's what M stands for. Number two, it depends on what the material is. Water is really good at absorbing a lot of heat to give away a little bit. So this C, it stands for what's called specific heat. It's how much energy it takes to make something go up or down 1 degree. And then the delta T stands for change in temperature. So again, how much heat is given? It's your mass multiplied by your specific heat and then multiplied by your change in temperature. I've got a table here in your notes of just common specific heats. So I talked about water before. I mean, it's really, really big, 4,180. So it takes 4,180 joules to make 1 kilogram of this stuff go up 1 degree Kelvin. And going up 1 degree Kelvin is the exact same thing as going up 1 degree Celsius. So this water, I mean, this is why water it's really cold in June, even though it's like 80 degrees. I mean, it takes a lot of time and energy to bring the temperature of water up. And then when it gets cold outside, it takes a lot of time for that to give away all that stored up energy back to the atmosphere. As the opposite of that, look over here, lead. Lead is really easy to heat, and it's really easy to get rid of its heat, to quote unquote cool. Like it's literally like 40 times easier to heat 1 kilogram of lead than it is to heat 1 kilogram of water. Like it takes 40 times the amount of energy. And this is why in your house, tankless water heaters are way more efficient. So those of us who have older tank style water heaters, you're constantly having to heat water, which is really energy intensive. A tankless water heater, it only heats it when you need it to. So when you turn on the faucet, it heats the water as it passes by. So you're not storing it at all times. So tank water heater, way, way, way less efficient than something like that. Let's go through an example problem using a couple more equations, but I'll come back to that. I want to do an example problem with energy transfer, and that's where I'm going to stop us for today. So it says, calculate the energy transferred when you put a really hot block of aluminum and you're putting it into water that's right around room temperature. So you'll notice that the water, it goes from room temperature and it goes up to 30 degrees Celsius. So let's do a little investigation with that equation that we did before. Q equals mc delta T. It wants to know, calculate the energy transferred. That's the letter Q. It wants to know how much energy is transferred. Well, we know the mass. The mass of the water, it says, is 1 kilogram. So the mass is 1 kilogram. The specific heat of water, if you go back to that, remember that table that we were just at? It was 4180. And it was joules per kilogram per degree Celsius or degree Kelvin. I'm just going to say degree Celsius. And then the change in temperature. The delta T stands for the change in temperature. So the temperature goes from 25 to 30. So this changes temperature a positive 5 degrees Celsius. Now, if you multiply 1 times 4180 times 5, and it's really important that you look at your units in this stuff because kilograms cancels off kilograms, degrees Celsius cancels off degrees Celsius, so you're left with joules. If you take 1 times 4180 times 5, you get 20,900. Or 21 kilojoules. That's how much energy has transferred. That block gave away 21 kilojoules to the water in cooling down. So we're going to continue with this in our next lecture tomorrow. But again, it's really important that you guys write this stuff down as I'm going through these definitions. Write them down so that you can call back to them another time.